When you stand at the base of the Great Pyramid and look up, the sheer physical reality of the structure is overwhelming. You are looking at 2.3 million individual stone blocks, stacked 146 meters high, assembled 4,500 years ago, without a single modern machine. The strangest detail about this achievement is what the builders left behind on paper. We have highly detailed ancient papyrus logs from the Egyptians, outlining everyday logistics. We know who showed up for work, how many rations of bread they received, and the exact manifests of boats bringing supplies down the Nile. Yet in all of these meticulous daily ledgers, there is a total void of engineering information. There is not a single drawing, a spatial map, or a recorded plan explaining how millions of multi-ton blocks were actually elevated. This complete silence in the historical record suggests that our most basic assumptions about how these stones were put together might be wrong. Modern humans suffer from an inherent additive bias. When we see a tall structure, we automatically assume it was constructed from the ground up, adding layer upon layer. This comparison shows the most common explanation, an external ramp. To keep the incline shallow enough for workers to haul 2.5-ton stones, you would need a 1.5-kilometer ramp. That requires more raw material and labor than the pyramid itself. Internal spiral tunnels aren't the answer either. In 2015, advanced muon particle scans tracked cosmic rays passing through the stone to map the interior. As this cross-section illustrates, they found large scattered voids, but zero evidence of a spiral ramp system. Even if the stones could be lifted, building upward creates an intense geometric bottleneck. As the work surface shrinks near the top, getting 4 lines to converge at a razor-sharp apex while working on a tiny crowded platform is nearly impossible to execute. If stacking stones fails basic physics at the bottom and precise geometry at the top, we are looking at the problem upside down. To find a different logic, we have to look 2,000 years later at the Nabatean civilization in the Jordanian desert. The Nabateans created 40-meter-tall structures, like this famous treasury building, by carving them directly into the solid cliff faces. By employing subtractive carving, they started at the peak and worked their way down. This approach turns gravity into an ally for removing waste, rather than an enemy for lifting weight. Independent researcher Yunchoi spent 10 years mapping the exact position of every stone on the Giza Plateau into a 3D model. His Unbuilt Theory suggests the ancient Egyptians applied this exact same subtractive logic. Choi's model reclassifies the Great Pyramids as massive subtractive sculptures, chiseled into their final form from the top down. The original geography of the Giza Plateau was not a flat plain. It featured natural, uneven limestone hills, which gave the ancient engineers a massive head start on raw volume. This diagram illustrates the proposed first step. Builders encased these natural hills beneath an oversized, wide, rectangular block of stacked stones with an integrated, gentle slope. Once they had this massive, elevated platform, the workers stood on the spacious top surface and carved the pyramid downward, chipping away the excess stone and pushing it off the edges as the work progressed. This eliminates the geometric bottleneck of the tip. Starting with a wide, flat surface makes it simple to perfectly align the corners and carve a flawless sharp point, with plenty of room for a large team to operate. Carving top-down replaces the impossible task of lifting thousands of blocks to a tiny peak with the much simpler task of dropping waste rock off the sides. Physical evidence for this descending platform sits on the adjacent Khafre pyramid. Recent drone surveys identified a repeating pattern of unusual angled joining stones scattered across the surface. These specific blocks act like lock pieces. Their placement proves that multiple teams of masons were working simultaneously, starting at the outer corners and moving inward toward the middle of the face to join their sections. An enormous ramp wrapped around the exterior would have physically blocked these corners, making it impossible for teams to start their work from those outer edges. The fact that workers consistently started from the outer edges and met in the middle proves they stood on an unobstructed, descending wide platform. But carving a pyramid out of a much larger rectangular mound creates an immediate logistical question. What happened to the roughly 2 million tons of excess rock that were pushed off the sides? This flowchart plots out the site's mass transfer, revealing a closed recycling loop. The scrap rock wasn't discarded. It was moved right next door to form the wide starting platform needed for the next pyramid. When you map out the total volume of rock needed to create the initial platforms and calculate what was shaved off and moved to the next site, the math perfectly balances. The final calculated volume of this entire multi-pyramid system matches the exact estimated weight of the modern Giza complex. The numbers demonstrate that the Giza Plateau wasn't a series of isolated construction sites. It was a unified subtraction engine. While this subtractive theory still awaits rigorous scientific consensus, the mathematical alignment offers a compelling lesson. If a mystery of this magnitude remains after 4 millennia, the obstacle might not be a lack of evidence, but our narrow perspective. Solving the deepest engineering puzzles often requires abandoning our most basic assumptions about direction, gravity, and the way things are supposed to be built.